Hi, I'm Max Forbes. I'm a software engineer at Google working on Kubernetes and also Google Container Engine, which is basically Kubernetes as a service. I'm coming here from Seattle, so forgive me if I'm a little bit jet-lagged and consuming coffee by the gallon. I want a diagram, so okay. So if you're not a convert about containers, just pretend that you love them for about the next 45 minutes or so. So I wanted to give a quick disclaimer that when I use we in this talk, I really mean hundreds of other engineers that have worked at Google's internal systems, or dozens of engineers on both inside and outside of Google who worked on Kubernetes. I hadn't heard of containers. Yes? Okay, I'm really nervous now about touching it.
Don't worry about it.
Okay. So anyway, this is my disclaimer. I haven't heard of containers until before last fall. So I'm really just sort of reiterating what I've heard about the past successes and failures of other cluster management systems. This is my really gross simplified timeline. That's pathetic compared to the ones you saw in the last talk. I'm hoping that my newness to this space and this talk will be helpful, because if you're not intimately familiar with it, I can have a good idea where you're coming from. So as a little bit of setup, this is probably a bad idea considering this great situation, but I'm going to launch a Kubernetes cluster using Google Container Engine right now. It takes a couple minutes. It really takes like 2 minutes, not like a half hour, but I'm going to get back to it later in the talk. So you know I didn't pre-bake anything. So you can see the type. This is and then do like container days processing. Hopefully this will. Okay, so we're creating a cluster. We'll get back to that later, once it's baked in for a while. Okay, so on with it. So Google uses containers. We run everything in them. So we run Gmail, web search, maps, all of our front-end jobs. We run all of our batch jobs, MapReduce, all of our internal systems. We don't run our detectors.
The other one's good.
Oh, the other one's still on. Great. Can you guys see the other one? Oh, well,
Yeah.
Great. I'll just keep talking. I'll keep nervously tapping the button here in case it comes back. So we even run Google Compute Engine, our infrastructure as a service offering, in containers. We run virtual machines inside containers. And we launch over 2 billion containers per week. So that amounts to roughly 3,300 every second. So we do a lot with containers. And when you're running that many containers, you end up encountering a lot of issues. You want your job to run in a smart place that can meet its demands. You want your job to run for as long as it needs to be kept alive. You want to know where your job is and where others can access it. You want to know what's part of your job, and you want to be able to scale your job up or down to accommodate load or lack thereof. You want to provide access control to your job for the many different things that people might want to talk to. You want to know what your job is doing, and there's a whole slew of monitoring information you probably want to know about it. You want to have some kind of metric about the status of your job, what's going on with it, how's it handling packets today, and a bunch more stuff. So in order to run those 2 billion containers every week at Google, we have a lot of custom tooling and infrastructure to handle the issues that I just talked about. And we looked around and we saw Docker was starting to get really popular. And we thought, wow, we know how to orchestrate containers. Not only that, but since we've been doing this for more than a decade, we also know a few ways not to orchestrate containers. So Kubernetes is born out of this thought process, because managing containers at production scale calls for a layer of abstraction that's amenable to human understanding. And that's kind of like the point of this talk, I guess. So I'll say it again. So managing containers at production scale calls for a layer of abstraction that's amenable to human understanding, and that's what Kubernetes attempts to accomplish. So I'll do a quick poll really quick. So by show of hands, how many people have heard of Kubernetes before? Wow, awesome. Okay. How many people have launched a Kubernetes cluster before? Okay, so a few. How many people are running their production services in Kubernetes? Awesome. Wow. More than 0. Great. That's surprising. Very cool.
It's a side project, so I'm not sure if that
Okay.
I do charge people money, though.
So I first want to show a brief overview of what Kubernetes looks like as a user of the system. So from a high level, we have some master components running in the middle here, orchestrating activities on a bunch of nodes. We have a command line interface and a user interface, both using an API to provide high-level goals to the master components. So you can see in the master of an API server and a scheduler. Don't worry too much about these, but you'll be seeing these boxes appear throughout the talk. So I just wanted to mention them. And the kubelet is the Kubernetes software that runs on it, sort of makes it part of the Kubernetes cluster. So user says, okay, turn off the projector. Is the other one on?
Yeah.
Okay. The user says, run X, where X is some set of containers. I'll run a couple of them, and they require some kind of memory and some kind of CPU. And then the master says, okay, I'll do that. And it says, okay, so where am I going to run those containers? And it finds a few nodes to run those containers, and it starts running them on them. The containers go and pull from some container registry, start running, and then report back to the master for status. The user can then query the API server and get back the status of the job. However, ideally, as a user of Kubernetes, all you care about is that you ask for X to be run and then it happens, and the rest is sort of abstracted. So for the rest of this talk, I'm going to spend a little bit of time going over the design principles behind Kubernetes, and then I'll introduce the core concepts of Kubernetes along with examples, and sometimes a bit of explanation for why it makes sense to do things this way. I don't know if Andrew is here. Which talk did you choose to go to? He sort of asked me to provide some pros and cons of alternate approaches, and I did that a little bit with pods, if you're familiar with the concept of pods, but I didn't go into too much depth on it, so it's kind of for him, so hopefully that's fine. Obviously it's for you guys as well. So before I go into detail about the components of the Kubernetes system, I'll give a high-level overview of some of the design principles that are driving this. Declarative is better than imperative. You want to tell the system what you want it to do, not how to do it. You shouldn't have to micromanage your machine or your cluster, and if you're running at scale, it's not even possible to micromanage. Control loops. So compare reality with the desired state and attempt to adjust reality. Control loops should make errors visible when something goes wrong, but it should also do as much as possible without any direction. Simple is better than complex. Each component should be only one thing to do well. That's going to be modularity, if we get the simple and good component thing down, we should be able to reuse and extend these pieces in new and unexpected and interesting ways. Legacy compatible, so this is a pretty important one. If you can get it into a container, you want to be able to run in Kubernetes. So you want to be as opinionated in as few places as possible. And this doesn't mean that running in production, every way of running in production is equally good, but we want to let you get your workload running and iterate from there rather than you can change one set before you can even get on. No grouping. So this is something I keep hearing about Borg, which is Google's internal cluster management system. It's sort of like the internal version of Kubernetes. I keep hearing that they got this wrong, and so everyone's really passionate about getting this right. I don't actually have any gripes about how Borg does it. I don't know how Borg does it, but I will say that the level of abstraction that Labels provides does feel like the right one. So I'll get more into this later when we talk about Labels. And then cattle is better than pets. So I'm not sure where this analogy came from, but the idea is that cattle are common and cheap, and you can teach a system to deal with them in a totally autonomous fashion. Whereas pets are delicate and unique flowers, which require the individual love and care of the sysadmin. And we want pets to be as infrequent as possible. We want projected blackouts to be as frequent as possible. And my jokes are just going to keep getting worse as this happens more and more. Is that one still on?
Yeah.
Perfect. Okay. This design philosophy is almost done, I promise. So open is better than closed. So we're not putting any private APIs into our components. Everything about Kubernetes is extensible and reusable. So design principles are great, and obviously they're important for the health and success of the system. But I want to focus more on this talk on what it's like to use Kubernetes. In Kubernetes, we've taken all sorts of the things that we want to tell a cluster to do and broken them down into some basic components that you can compose together to get the results that you want. And the part about Kubernetes that is tough to understand, or that's tough, is that there's basically 5 concepts you have to understand off the bat in order to get a sense of what's going on. And it's kind of tough to go over in a presentation like this. A lot of you guys, most of you have at least heard of Kubernetes before. But I'm going to have to front load you with a bunch of information and then start looking through the uses. The good news is there's only 5 concepts or so, and they're pretty intuitive. You've probably seen them in other forms before. So I'm going to introduce them one by one with some examples. And I think as we make it through, you'll start to see the power of composing these pieces together and what you can do with them. Other one's on. Okay. So without further ado, we have concept 0, a container. So I cheated here. You already know this one, so I didn't count this one. Docker sort of our de facto container format, but we're supporting my ones as well. So concept 1 is a pod. A pod is a group of co-located containers. You can think of it like a pod of dolphins. I'll go into more detail on this in a minute, but I just want to run through it. A controller. This is a term for anything that implements that observe, rectify, repeat loop that I mentioned a few slides back. It's a good design principle. This might be familiar to you if you've ever worked with low-level robots. It turns out Brendan Burns, one of the founders of Kubernetes, was a robotics professor before joining industry. So first up is pods. Cluster, IP, and so I want to spend a bit on pods. You really need this as part of your system. And the explanation that I was originally offered was, well, we use this all the time internally at Google, and it's really important. Which is, to be fair, a pretty compelling argument, because it's Google, right? So you kind of believe them. But it's not that satisfying. So the first thing that helped me to be convinced that pods are a big thing were more examples, so I'm going to give you a couple more. We already saw this example of a file puller and a web server. So in looking at this, I thought, well, couldn't your cloud provider just provide a file puller as a service? And the issue with this is that your cloud provider needs to write and maintain all sorts of different pullers for the different places to get content, like different content distribution systems, Git, Imperial. And it's much more feasible to have each of these file pullers be built and maintained as an independent container. The other example that helped convince me is the adapter pattern. So imagine you have some C program that most use services stuff. Pods really aren't anything crazy. They're just admitting that sometimes you want 2 or more things actually running together on the same machine, and you always want that to be true. I'm kind of beating a dead horse here, but there's just a couple more slides on this. So there's alternatives, and there's questions about this. So why do we choose a single IP per pod? That's pretty simple. That's just because it eliminates port mangling. That dramatically simplifies wiring applications together. I'll talk a bit about this more with services, but basically Borg internally does support mangling, and it apparently just caused hell, so people decided not to do that. So you could, why don't you just put everything in one container if you need them to run together? This has several disadvantages. So one is transparency. You want resource monitoring to be done by the infrastructure. You don't want to do it yourself. It decouples software dependencies. It's better to rebuild and deploy individual containers than to have them live in one monolithic container. Ease of use. You don't want to run your own process manager and worry about signal and exit code propagation. And efficiency. Containers can be lighter weight when you're separated. And why not choose something besides pods? So why not just try to co-schedule everything? Well, you want to schedule either all of your containers in a pod or none at all. You don't want to schedule one of them and find out there isn't space for others. But even if you say, okay, you have to schedule them together, you basically have a pod, but without the other benefits of pods, such as, I won't go into too much depth in these, but resource sharing, IBC, I already talked about shared fate and simplifying. So I hope that deep dive was somewhat useful. I'll talk a bit more about the details of the pod lifecycle, and then we'll round out to the rest of the concepts. I'm spending a bit more time on pods than other ones, because I think this is kind of the more controversial one, though I'm not totally sure. So here, remember again, pods are cattle, they're not pets. So if a pod dies, say because a machine goes down, a controller is expected to replace the pod with a new pod. And pods have phases. Pending means not running yet. It could mean the scheduler can't find a home for your pod, or it could mean that the Docker pull is just taking a long time for some reason. If your pod seems like it's staying pending for a long time, you want to look at events to see what's going on. I have a slide about events later on. Running means that the container is well started at least once, and the kubelet is going to restart them if the policy asks for that. And succeeded and failed are pretty much what you can imagine. You'll only ever get to the succeeded state if your restart policy doesn't require infinite restarts. So this would be a job that you want to complete, like a batch job, rather than a service that you want to keep alive. That's an in-serving job. There's a couple more notes, which is that pods are not rescheduled by the scheduler or the API server by design. And that's the job of replication controllers, which I'll get to in a second. It's by design to keep the scheduler simple. And there's finally a little note about that apps that are using these things should keep how pods run in mind. Okay, so we're finally done explaining pods, but pods are kind of the bread and butter of the system, so the other concepts build on how to use them effectively. So for instance, the other primitives need a way of identifying a set of pods to talk about or operate on, and that's where labels come in. Every object in the Kubernetes system has some metadata which follows a common format. You have a namespace, a name, creation time, labels, and annotations. The labels are focused around identity and they're queryable. Here are some examples of labels just to get your creative juices flowing. So I'll use pods in these examples, but remember labels can be applied to any object in Kubernetes. So you can imagine that you have a label for release, and so you can query your pods based on which ones are your stable release or your canary release, an environment, so your dev pods, your QA pods, your production pods, which tier your pods are, if they're your front-end pods, your back-end pods, partitions, tracks, these sorts of things. So as I mentioned before, labels are queryable, and you use a selector for doing that query. That's concept number 5, for selecting objects by their labels. So it's just like a SQL select where statement. Let's see an example. So this is where I really want both sides to work, because there's a diagram on screen. I'll zoom in a little bit. Or I'll just keep going. Okay. So imagine I have, I want to see all the pods that are involved in running my Nifty app. So I can do this. I can say select all pods where app equals Nifty. But what if I just want to talk about front ends? I can do the selector that asks for both app equals Nifty and role equals front end. I do the same with back ends. Or maybe I want to talk about everything in my dev setup instead of the test setup. So you get the idea here. So now that we have pods and selectors, we can talk about the components that operate on pods. Now recall again that I said pods were cattle. This is one of the points I'm hammering in. And if one happens to die, it's replaced by a controller. A replication controller is the component responsible for doing that. It's got a pod template, and it's got a desired number of replicas. And it just sits there watching pods and the system start and stop. And it can request new instances of the template, or destroy pods if it sees too many. So typically you'll want to run your pods by creating a replication controller instead of directly making them. And that gives you a layer of automation and self-healing. Now replication controllers use the selectors that we just talked about to identify the pods that they own. So for example here, these blue thingies represent some pods that match our replication controller, selector. So when a replication controller makes a new pod, it adds a random suffix to the pod's template name. And that's why we've given these a nice hex value, like F0118. This is a naming system appropriate for cattle, not pets. Oops, it looks like someone left node 2 out during a thunderstorm. So replication controller sees this in a pretty short amount of time.
Same thunderstorm.
Same thunderstorm, just look at this projector. There should be really low latency between the lightning strike and the replication controller noticing this and responding. So you can see, if you're looking at the other projector, that the current state is now 3 pods and the desired state is 4. So it makes another one. The scheduler finds a home, the kubelet starts a new pod, and we're back to the current equals desired state. Sometime later, someone brings node 2 indoors and reboots it, and now the replication controller has the opposite problem. It's got 5 pods, and it only wants 4 of them, so it has to kill something. And these are cattle, so it doesn't matter which one it kills. So you know now about pods and how to run a managed group of pods, and how to label them and select them, and how replication controllers work. But how do you talk to pods, and how do you compose pods into coherent applications? The answer to that is services. But before we talk about services, we should say a word about networking, because services are really just an abstraction of networking. The IP addresses we give pods, now remember we give one pod, one IP address. They're mostly real, they're routable within the cluster. We require this of your network fabric. This is one of the things that we are called a community about, but this is one thing that we require. And if you're not running a GCE, you can look up something called Flannel. There are many ways of meeting this requirement. We don't do dynamic port assignment. So the thing that I'm supposed to highlight in this slide, someone else wrote, is really highlight that we don't do dynamic port assignment. Or really screwed this up because we did dynamic port assignment there and it got really hairy. So again, this is it's other people's anecdotes, but apparently dynamic port assignment makes services really messy. We'll see a little bit in an upcoming slide why that might be true. So services are an abstraction with 2 parts. They answer the question, what implements this application? And the question, how does the rest of the cluster see this application? So let's go to an example and come back. Say you've written a nifty app that we've been talking about, and you want the rest of the cluster to be able to talk to your app. So let's say maybe this app translates English sentences to Klingon or something like that. And obviously that's going to be very heavily used, so you need more than one container running it. You're going to make a service object to tell Kubernetes how to direct traffic for this translation app. Your service will have a selector to identify all of the pods that are running your application. That's the pods that can handle traffic requests intended for this translation application. You tell the service what port on these pods to send traffic to, and then the Kubernetes system makes your service its own virtual IP address and makes it available to DNS on all the pods in the cluster. So there's a lot of information on this slide. I will break it down in a sort of step-by-step example. So there are more complicated things you can do with services. There's a way to make a service that directs traffic outside of your cluster, like if you discover that someone else already wrote a great English to Klingon translator, and it's running out of the web, and you want to start using that instead of your own, you can modify the service description a little bit to do that. Or suppose that you want your app exposed outside of the cluster, like you want to compete with the other translation service. Then you set up a public IP address for your service. That was a bit fast, so yeah, let's step through an example here. So here you've got your API server, which you can think of as running on your Kubernetes master, and you've got a queue proxy that's waiting for something new to happen. So it's watching services and endpoints. So a user comes along and says, schedule me these pods for my nifty app, this English to Klingon translator. The pods are called pod 1. I apply these labels to it, app nifty, and it's exposing on port 9376. So the system makes it so, and the pods are run. Now behind the scenes, we probably declare a replication controller so we can make sure that the pods stay up, and we can scale the numbers up and down and all that jazz. But the important part here is that you can see the pods for the nifty app each have their own IP address, and they're all exposing port 9376. Now here comes the service. The user says, make me a service. And the service is this nifty service, and you can see the selector is exactly the label that we've applied to the pods in the nifty app. The service is going to have a port IP of 10.9.8.7 and exposed on port 80, and the target port for the pod that it's talking to is 9376. The queue proxy is watching for new services, so it says, hey, there's a new service. It's going to listen on some random port X, and it's then going to write IP tables rules to redirect anything sent to 10.9.8.7 on port 80 to localhost port X. So stick with me here, it should make sense in a sec if it doesn't yet. So the queue proxy also sees that it's got new endpoints that match the service selector. And here you can think of the service as being linked to these pods. It's like the backend for the service. So now let's hear how it works in action. A client comes along and connects to 10.9.8.7 on port 80, and this gets redirected to port X, localhost to port X. The client connects to port X, and that's proxy to one of the pods. That's actually So we've gone through the core concepts of pods, controllers, services, labels, and selectors. And I'll talk now about a few more pieces of Kubernetes that helps in running and debugging applications. The last Kubernetes itself object that I'll talk about is events. And this is how you get a feel for what's going on in your cluster. If Kubernetes is unable to pull the image for your containers, or if it's restarting them, you should see you'll see events for that. If your node loses connection, you should see an event for that. When your schedule assigns a pod to a node, you should see an event for that as well. So we make events for both positive and negative things. So if something's taking a long time, like your pod is standing pending for 6 hours, you can at least see the last thing that did happen to your pod. We run some add-ons. I'll go through these somewhat briefly, but basically we can launch a bunch of stuff as pods in your cluster to help you out. And so like heap store and C advisor, collect usage stats. There's a UI that you can look at some of this data. And also logging is another add-on that we started by default. So this lets you go and find the logs from that one time that your Klingon translation service crashed. And if I haven't completely screwed up the timing, I don't know how late I started, but I have a short demo here that I'm going to go through live because that's always a good idea. So remember iTurn. Great. So it worked. I think it looks like it worked. So I created a Kubernetes cluster running on Google Container Engine, which is again just Kubernetes as a service. I'm going to copy this line just to set queue control points to that cluster. Cool. So now what I'm going to do is I'm going to show a small application that makes use of a few of the concepts that we've talked about. So I'm going to turn up the UX for this demo. It's just a simple proxy to the Kubernetes API server. I'll actually type this out just so you know what's going on. So this is just pointing to kubectl. It's basically a shell script that finds where kubectl is. Kubectl is the command line client for Kubernetes, so it's how you talk to the API server on the server. So I'm going to create a thin proxy that basically just allows me to have a simple JavaScript thing that hits kubectl and then or hits kubectl and then proxies those requests to the API server, so JavaScript can also talk to our API server. And I'm going to do the static files directory. Is this big enough for people? Can you guys see my background?
Yes.
Okay, cool. So it's starting to serve. Awesome. So that's not the interesting part. I should have wrapped my. I'll send to the next slide. Anyway, okay. Let's. Okay. We're going to run a replication controller now. Which, if you remember, replication controllers spin up pods and keep them alive if that's their policy to do so. So I'm going to again talk to kubectl, and I'm going to say create. Oh no, there we go. Create -f. Head on Kubernetes. You can do this exact thing if you want to. You can play along here. And we're going to do an this replication controller. So actually, before I do that, I'm just going to show what that is. So this is just a replication controller. You can see we specified the image down there. And we have 2 replicas. It's only serving 1 container. A lot of time going on there. It's fairly simple. It looks like there's some repeated fields, but it's kind of necessary evil of replication controllers. So anyway, I've saved that command, so I'm just going to create that. And then you should be able to see that's the visualization of the pods that are running. So the pods have already been scheduled, and they're up and running on the cluster. So the nodes, it should show the host. Yeah, so these are different machines in the cluster. So this is one virtual machine, NSC, and another virtual machine, VCMY. And these are the pods. You see we've named them like cattle with these postfixes after them. You can see the image through there. So,
Don't worry, the other one's still
oh,
on.
that's still up. Cool. So that's pretty cool. We're going to scale the controller up. So we can run cluster Kubernetes. We're going to say scale replication controller. Update demo. And we're going to say replicas equals 4. So it's already found that the desired state was 2. Or the desired state was 4. It only had 2 running, and it scheduled 2 more pods. They ended up. It looks like they're evenly distributed on the nodes. We've got 2 on one node, 2 on the other. Actually, I kind of like scaling it up to a bunch more. So does anyone have a number they want me to?
75.
26.
26. I'm going to do it before someone mentions something like the tens of thousands. 26. I haven't tried that. So pretty quickly, and the pods themselves are serving these images. So we see we've got, I will trust that this is 26. We'll wait until the images are all loaded. But yeah, so it just scheduled 26 pods or 26 containers running in the cluster. And screen's black. So we're going to, I'll scale it back down. So the next thing involves something that happens per pod. So I'm going to scale it back down to 4 just so we don't have to sit here for hours while we deal with 26 of these pods. So it's back down to 4 if you can't see. So the next thing I'm going to do is a pretty nifty feature that we've put on the client, which is a rolling update. So this rolling updates the Docker image that you're using. So you can imagine that you have like version 1.2 of your service and you're rolling out 1.3 and you want to review this incrementally. So what we do is we have this old service running at this many, and we start with a new service running at this many, or replication controller. Sorry, I need to be precise with my words. Replication controller, and then we sort of scale them like this, so that you end up deleting, you end up creating a new pod and deleting an old pod at the same time, and then they kind of go up and down. So I think I'm using for this new one. So you can see these are cute little fish. I looked up how to pronounce nautilus yesterday. I hope that's correct. And so we're going to scale to use this new image, this new replication controller. So very similar. Notice it doesn't have a number of replicas specified, so that's going to be determined with the rolling update. It's just going to turn it up to the number that the replication controller replacing has. So I'll go ahead and start typing this. So we're going to use again view control as the mainline client, and we're going to call rolling update. We'll do it over 10 seconds per pod, just so we can see it happen. And I'll specify the file of the new replication controller. Oh. Yes, thank you. One knows this better than I do. So now let's watch as kittens start appearing and fish start dying. This is really like the best visualization we can do against the system. I wish I'd worked on computer vision or something. No, I'm just kidding. This is great. Okay, well, you can't even see it now, so. Okay.
The other one's still.
Okay, cool. So the other one's doing it. So you can see fish are dying, kittens are coming out. They're both cattle, so we don't really care about them.
Both cattle.
They're cattle kittens. Don't help either or anything.
Careful, you're gonna turn into a meme.
That's right. So they're going on every 10 seconds. I should have done this over fewer seconds in hindsight. It's like we still have.
Does
more
it
fish. Oh, there goes
watch
it.
the jobs for help?
Yes.
While it's doing
I believe so. I think it doesn't create a new pod until the other one is, or it doesn't delete a pod until the other one is. And one last fish remaining. Oh, waiting with bated breath here. Okay, cool. Now it's done. So we've updated to our kittens slowly, but surely, and then the replication is done. So now the final thing that we're going to do is we're going to do kind of a shortcut for killing all the kittens. So we're going to stop the replication controller. And so we say stop RC, and then the update demo. And what that does is it first turns the number of replicas down to 0, so what we call the pods, and then it actually deletes the controller itself, which is needed so that they don't. Cool. That is. Go back to my slides. So that's my demo. I have a little sales pitch, I guess. Kubernetes is open source. That should be, so what I've shown you should be enough to start using Kubernetes. Looks like all of you have heard of it, which is awesome. So maybe you didn't need that. Hopefully some of it was useful for you. So as far as next steps for Kubernetes, in case you're curious, we're closing in really fast on the 1.0 release. So our big focus right now is just hammering the living crap out of it to make sure that it actually works and stands up. We love contributors. We hang out on IRC all the time. So if you're at all interested, we'd love to hear from you. If you'd like to try it out, I recommend that you download it and go through. There's a ton of examples in the examples directory, just like the one that I did, that show off different pieces of the system and how they work. Thanks so much for listening. That's all I have. I think we started late.
Yeah, we have 3 minutes.
3 minutes.
For questions.
Cool. There's a 50% chance we'll be able to answer any question. Yeah, go ahead.
A couple of questions. So,
Yeah.
pods is the smallest. Is that the smallest unit that can be scheduled?
Correct. It's the atom schedule.
So, what Kubernetes entity is actually doing the scheduling, and what what criteria is it using to schedule?
So I believe the scheduler is pretty simple right now, and the scheduler is running on the master, so that decides where the pods.
Is it just called a scheduler, or is it?
Yeah. Let me go back. I can rewind. There we go. No, that's fine. Yeah. So there's a scheduler running on the master.
Okay.
Currently, just have one. We're working on high availability master soon, but it's running on the master. It decides where the pods go initially, and it basically just says, yeah, is there enough like CPU and RAM for me to run this pod there? So there's probably more. I haven't looked at it closely, but I know that it at least looks at those things, because when you ask, you definitely have to specify like I need this much memory.
It's not necessarily trying to balance across nodes based on CPU utilization?
I imagine it does some of that too. So I know almost nothing about the schedule. It seems like something you probably want to do. That like if you like think about scheduling, like what would I want to do with scheduling? You probably want to balance a little bit. So I think it does do that as well. I know it's not like a really sophisticated scheduler, nowhere near like what they have internally, or probably in Mesos, for example. But yeah, it's dead simple right now. Part of it's by design. So for the restarting of pods, it's kind of happens independently with replication controllers and kubelets. But yeah, I'm going to answer your question. Yeah.
What about the isolation between individual pods? How are brief sources enforced and how strict?
Yeah, so I don't know much about that. I know that as far as isolation goes, we're using Docker containers. So if you're talking about security isolation, there's a reason we run everything in virtual machines right now. Yeah, we don't, but basically, yeah, you have what Docker has. Yeah.
How are the proxies scaled?
The kube proxies, you mean, or like the services, or? Yeah, so there's a kube, so I can answer this in a pretty basic way. I know that there's a kube proxy running on every to redirect the traffic. So basically every node knows about all the different services that exist in where to send traffic. So that's kind of like a way of scaling, basically, it scales throughout the nodes. Beyond that, I can't answer anymore.
Sorry to interrupt, guys.
Yes.
One more question. Then everybody over into the coaching room. We're done. Thanks, guys.
One. Okay, we'll call
Oh,
it.
that was
Thank you
it.
so much.
That was it.
Awesome.